First, I'd like to thank the organizers for the opportunity to give this talk, also for bringing this nice workshop to Natal. So this is the plan for this talk. Basically, the message of this talk will be that if you consider the combinations of strong correlations and strong spin-orbit coupling, we can get some new strongly correlated phases that are described by new spin models. And I'm going to illustrate this idea by talking about the case of this compound. This is barythium molybdenum oxide, and propose that this is some kind of what we call a chiral spin orbital liquid. And then I'm going to discuss our attempts to characterize some properties of this chiral spin orbital liquid. So this will be mainly dynamical response functions. So in this talk, dynamics means dynamical correlation functions that are interesting for experiments like NMR, neutron scattering, or inelastic X-ray scattering. And the main person behind this work is my PhD student, William Natori, who's based at the University of São Paulo in São Carlos. And it was also done in collaboration with Maria Daghofer from Stuttgart. So let me just remind you about some basic facts about magnetism in Mott insulators. So a Mott insulator is something you can describe by starting from a Hubbard model and taking the limit of very large U, very strong repulsion. And in this case, you can think that charge fluctuations are frozen, and the interesting low energy physics is only in the spin degree of freedom. So you can think that there is one spin 1/2, let's say, at each position on a lattice. And if you start from the Hubbard model and you take the large U limit, the natural spin model that you get is the Heisenberg model with antiferromagnetic exchange interactions of positive J. And if you put this model on a bipartite lattice, the standard thing is to get a ground state that is Néel ordered, which means that the ground state breaks spin rotational symmetry spontaneously with this kind of up-down and up-down pattern. And then you can also talk about excitations on top of this kind of ground state, and the excitations would be quantized spin waves that we call magnons. So that's the conventional story. What I want to tell you about is about quantum spin liquids, which are essentially come from denying what I said before. So in my previous example, you could say that the Néel state is some kind of spin solid in the sense that it orders, it breaks some rotational symmetry. A quantum liquid of spins would be something that does not order. So one defining property is the absence of log-range magnetic order, even at 0 temperature. And also the elementary excitations you get on top of this ground state are kind of exotic. They would be spin 1/2 particles, which can be described by many different theories, but sometimes called spinons. And this idea goes back to Anderson's proposal back in the 70s, that when he proposed this so-called RVB, or resonating valence bond state, the idea is basically that you can, if you take just 2 spins and you can write a rotationally invariant state just by taking the singlet. If you go to the many-body problem and you write down a coherent superposition of singlets between all pairs of spins with symmetric amplitudes, you can construct a ground state of the many-spin problem that is rotationally invariant. This would be a quantum spin liquid. And then you can discuss excitations on top of this state and convince yourself that this would be spin 1/2 particles. And then the question is, where can we find quantum spin liquids in nature, say? The conventional wisdom that has been accumulated throughout the decades that people have been working on this problem is that you can still think just about the Heisenberg model, but put it on a lattice that is geometrically frustrated, that is formed by, say, triangles. And then frustration here means that the antiferromagnetic exchange interaction cannot be satisfied locally for all pairs of spins. You cannot, because the lattice is not bipartite, you cannot impose a simple Néel pattern as a guess for the ground state here. And then in this case, you might think that the ground state might choose not to order and you get a quantum spin liquid. And indeed, there is recent experimental evidence, particularly in this compound here, Herbert-Smith-Tite, which is well described by the Heisenberg, antiferromagnetic Heisenberg model on the Kagome lattice, this lattice constructed by coordinate shared triangles, that this is a good candidate, perhaps the best one, for a quantum spin liquid. And the usual signatures here is that people look at various properties like magnetic susceptibility, specific heat, down to very low temperatures, and find no sign of of phase transitions, no sign of magnetic order. You can check that with neutrons, and then you start thinking about whether if that could be a quantum spin liquid. And in fact, there's also numerics done on this problem, the Heisenberg model on the Kagome lattice. The last word, as far as I know, on this problem is that it seems that the ground state of this model is a quantum spin liquid with some kind of gapless spectrum that has Dirac fermions coupled to an emergent U1 gauge field. So this is just to give you an idea of why theorists are interested in this problem, is because the theories that describe quantum spin liquids are usually very exotic. You can get some emergent quasi-particles like fermions in a system where you only had spins to begin with, and also emergent gauge fields. Here I'm just throwing, just to add to the experimental evidence, that usually very good test of quantum spin liquid behavior is neutron scattering. So if you do inelastic neutron scattering, you can probe the excitation spectrum of this system, and this was done on this compound. And usually if you have magnetic order, what you expect to see is a very sharp, well-defined peak that tells you about the dispersion relation of the magnon. But in a spin liquid, what you get are usually this kind of blur. It's like the energy is always distributed between pairs of these spin-on half particles of the spin-ons. And it's a blur, but it's some special kind of blur that you can try to fit with some different kinds of theories. Okay, so that was the traditional way to look for spin liquids, geometric frustrated lattices. A new route that we want to explore here is this idea that you can combine strong correlations and strong spin-orbit coupling. So for people coming from a strongly correlated electron systems community are usually interested in this axis here. This is interaction strength, U over T, say in a Hubbard model. And along this axis, we're used to talking about a Mott insulator, a metal insulator transition induced by strong correlations. But recently, there has been a lot of emphasis in condensed matter physics about the effects of strong spin-orbit coupling. So even along this axis here, if you neglect interactions, there is some interesting physics, because here you could go from a trivial band insulator to a topological insulator. And then, of course, people started wondering what happens if you go along the diagonal here, if you combine the two things, and then you can get all kinds of, these are theoretical predictions, really. There's not much experimental evidence there, but there are predictions for many kinds of exotic phases, like axion insulators, vial semimetals, and so on. What people show on this diagram usually varies from paper to paper, so don't take too seriously the positions of these things. But what I want to emphasize here is that in this kind of schematic phase diagram, there is room for a spin-liquid phase when you combine strong correlations and strong spin-orbit coupling. And where do you get that combination? So usually, if we want strong correlations, you take transition metal oxides. So here, in this case, we also want strong spin-orbit coupling, which means that basically we go down in the periodic table, and we're going to talk about materials that have, say, 4d and 5d electrons as the active magnetic ions in a given compound. And let me just comment that, yeah, so as you know, if you go down here, you usually get stronger spin-orbit coupling. And sometimes our intuition about spin-orbit coupling is that if you add it as a perturbation, say, of a system that has described by Heisenberg model, you get extra terms that break spin rotational symmetry, SU2 symmetry, just because the spin is now coupled to orbital degrees of freedom, for which you only expect to have discrete symmetries, the lattice, the crystalline symmetries. So if you break a spin SU2 symmetry, shouldn't we get something that is more classical, like with Ising-type interactions? So how can you get quantum spin liquids from this kind of system where SU2 symmetry is broken? So the answer is really counterintuitive. So let me first give you an example. This is a celebrated example that got a lot of people interested. The case of the iridates. So here's sodium iridate. The interesting thing about this material is that it has the magnetic ions are iridium 4+, that has 5 electrons on a D shell. And these iridium ions are distributed on a honeycomb lattice, and each iridium ion sits inside a cage. It's a oxygen octahedron, so it's subject to a crystal field that has octahedral symmetry. And the first thing people do here is say, oh, okay, let's work out what's the local Hilbert space, or is the effective spin degree of freedom in the presence of a crystal field, taking into account a strong spin-orbit coupling. Remember, iridium is a 5D, so it's quite heavy. Spin-orbit coupling is of order of a fraction of electron volts. And also, of course, the fact that it's strongly correlated, so you should get some kind of Mott insulator. When you work this out, you see that with 5 electrons, you're going to have a single hole in this energy level here. There is an effective J equals 1/2 degree of freedom. We talk about J here, that's the total angular momentum, because it's a combination of the spin magnetic moment or spin angular momentum with the effective orbital angular momentum of these d electrons, in particular of the T2G electrons. Yeah, so effectively you can think that you have some kind of spin 1/2 degree of freedom distributed on this honeycomb lattice. But then people worked out what the effective spin model would be. Then you start talking about exchange processes where you have virtual transitions where the electrons visit the other sites. You do perturbation theory to order T squared over U or higher. This was done by Jacques Kelly and Kaliulin, who found out something very interesting, that the effective model for this kind of material, for the iridates, with, I should emphasize, edge-sharing octahedra, is what is known from theory as the Kitaev model. The Kitaev model is a spin model. For here written, it's in terms of Pauli matrices, so this is a spin 1/2 system. And you can see that you have a spin 1/2 degree of freedom at each lattice site, but the interaction between nearest neighbor spins is not Heisenberg type, but rather you get an Ising type interaction that depends on the direction of the bond. So what we do here is we divide up the honeycomb lattice in terms of, so first of all, there are 2 sublattices. They're painted green and red here. And for each lattice site, there are 3 types of bonds or links. There is an X link, there is horizontal, then there is a Y one, there is rotated by 120 degrees, and the Z one. And when you look at the interaction between nearest neighbor spins, say these 2, here you would switch on sigma X interaction because it's the X link. But if you look at along this direction here between these 2 spins, you switch on sigma Y, and so on. And you cover the lattice with this kind of local Hamiltonian. Here, the interesting thing is that actually the honeycomb lattice is bipartite. So it's not frustrated, geometrically frustrated. But the frustration comes from the fact that the interactions are bond dependent. So the direction in which you couple the spins depend on the directions of the bonds. So in this case, this guy looks to a first neighbor and say, I would like to order along the Z direction. The other one would like to order along the Y direction, and the system just doesn't know what to do. And so this is just an argument for why we could expect the system to have a quantum spin liquid ground state. And in fact, Kitaev proposed this model way before people started talking about iridates, because he was interested in this model, because this is exactly solvable. And we know the answer for sure. And the answer is that you can find the exact ground state of the of the Kitaev model using a representation of spin 1/2 operators in terms of 4 Majorana fermions. So this would be the 3 components of the spin operator, A equals X, Y, or Z, and then we're going to use 4 Majorana fermions. These guys are Majorana fermions in the sense that, first of all, 2 different operators with different flavors anti-commute, like fermionic operators, and they are Majoranas because they are Hermitian. So like people say, the particle is equal to the antiparticle. So you can check that this representation reproduces the SU2 algebra for spin operators if you impose also a local constraint, that these Majoranas that you define at each lattice site are not all independent, but the product of them with a factor of I has to be 1. And this is because you need this local constraint because the the Hilbert space to which we're mapping the spin problem is actually larger than the spin 1/2 Hilbert space by a factor of 2. So this is a kind of a local constraint that tells you about something about the gauge structure of this theory. There's also a gauge field here. And in fact, if you use this representation, you plug this into the Kitaev Hamiltonian, what you find is that a bunch of these, essentially the x, y, z fermions become static variables. You use them to define local conserved quantities. And the eta 0 fermions are just free, they behave as free fermions hopping on this honeycomb lattice. So from this, you can show that the expectation value of the spin operator in the ground state in the thermodynamic limit is 0. And the excitations, the elementary excitations, you can also talk about the spectrum, are these deconfined Majorana fermions that move on the lattice. And for fermions on the lattice, you get this kind of band structure that is familiar from graphene, where you get two bands that touch here at 0 energy at one point that is a Dirac point. So this is an example of a gapless spin liquid with a Dirac spectrum and Majorana fermion excitations. Well, then we can go back and ask if this kind of Kitaev model is realized in nature. It turns out that the people started thinking about the case of sodium iridate. And the true story is that sodium iridate is, of course, not just the Kitaev model, but Kitaev plus perturbations. And it turns out the perturbations take you out of the spin liquid phase. The sodium iridate falls into an ordered phase. There is some kind of a zigzag pattern. So that's unfortunate that nature didn't put this material in the correct point for us to find a quantum spin liquid yet. We can start thinking about our alternatives. And people are really thinking about different materials that might show Kitaev magnetism, as it's called at the moment. So from here, I want to go in a particular direction. About like I told you, the case of sodium iridate was a single hole in a J equals 1/2 level. So let's think about the complementary case here. Let's say I have only one electron instead of a single hole in the same kind of crystal field and combination with a strong spin-orbit coupling. So in this case, so sodium iridate would be like the single hole up here. So now I'm going to talk about the case where I put a single electron, like a D1 electron, which will be now in this lower energy manifold that is a J equals 3/2 multiplet. Our motivation for thinking about this goes back to this paper, because there are actually some materials that are well described by having J equals 3/2 magnetic moments on some lattice. And this is the case of ordered double perovskite. Double perovskites are materials with this kind of chemical formula. The important thing here is that you have your magnetic ions. Some of these materials are Mott insulators, and the magnetic ions would be the B primes that sit here and say in this purple regions. These are octahedra again, which define, they form an FCC lattice. So the effective spin model here would be J equals 3/2 on the FCC lattice. And at the time, we tried to work out the spin model for these materials and see what kind of phases we could get, and try to fit in some of the materials in this family into this simple, it was a mean field phase diagram. And we got some interesting ordered phases, like a ferromagnetic phase ordered along 110 direction of the FCC lattice. There was an antiferromagnet whose primary order parameters was an octopolar moment of the J equals 3/2 states. And something we learned at the time was that if you take, so this would be a phase diagram with some kinds of interactions that don't matter very much for now. But if you take some particular limit where there is only dominant antiferromagnetic exchange interactions, you can compute quantum corrections to the ordered states, and it turns out that there is this corner of the phase diagram that you would find strong quantum fluctuations. And that's usually a sign that it might destabilize the ordered phase and get a quantum spin liquid. And indeed, in this family of materials of double perovskites, there is one guy, this barythrium molybdenum oxide, that is a good candidate for a quantum spin liquid. Let me tell you why. So here's some experimental results from different groups. Like I said, usually you look at the various properties as a function of temperature. First thing is to rule out phase transitions. So people have looked at susceptibility, heat capacity, neutron scattering, NMR, mu SR, and found no evidence of magnetic phase transition, no order. Also, and this is important, no structural transition. This material remains cubic. It doesn't go like tetragonal or anything, down to 2 Kelvin, which is kind of unusual. Yes, so from the high temperature behavior of the magnetic susceptibility, when it can extract a revised temperature, and usually people characterize these candidates, spin liquid candidates, in terms of a frustration parameter, the ratio between the revised temperature and the temperature at which this thing would order, and this is larger than 100, so this is again a good candidate. Another interesting point is that from the specific heat, you can compute the released entropy out to some temperature scale, and there is some agreement between the prediction from a J equals 3/2 quadruplet that you find that the variation in entropy is R log 4, so it's a sign that there are 4 states per lattice site, as we would expect from that single ion picture. Also, mu-SR gives some evidence for spin liquid behavior. In this paper, they comment that the behavior is similar to Hilbert-Smith type, the best spin liquid candidate that I mentioned before. Yeah, so this is a specific heat. I'll come back to this plot later. Okay, so what does the spin model look like in this case for J equals 3/2 moments? So this is going to be a little bit more complicated than the Kitaev model, simply because now we have more states. So for J equals 3/2, we have 4 states, and a convenient way to represent these 4 states is to trade the J equals Jz eigenvalue for 2 pseudospins 1/2. So that's 2 times 2 also gives us 4 states, and we do some mapping like this, like the 3/2 states we map to plus, it could be plus 1/2 flat, or just plus, and so on. This is chosen so that the states here, they are conjugated by time reversal symmetry, they differ by the first eigenvalue. So this would be the Sz eigenvalue. I'm going to call this the pseudo spin. And they have the same eigenvalue for the second operator here, the tau z. I'm going to call this the pseudo orbital. These are all pseudo because remember this is a system with strong spin orbit coupling. So these things are already coupled, but this is something, S here is something that behaves like spin, and tau is something that behaves like an orbital degree of freedom. And if you use this notation and represent the J equals 3/2 operators in terms of S and tau pseudo spin operators, this is the effective spin Hamiltonian. And here, notice there is some coupling between the pseudospins that is isotropic, Heisenberg-like, but also there is some dependence on the interaction here on the orbital or pseudo-orbital degree of freedom. And these are tau x, alpha and beta are x, y, or z. So these are operators that you choose depending on the plane on which the pair of sites ij are. So say 2 sites on the xy plane, you should choose tau xy, which is tau z, written in terms of this pseudo-spin. And for the other planes, we take other combinations of tau z and tau x, which you can recognize. These are 120 degrees rotation in this tau x, tau z plane. So this is a kind of model that appears a lot in the context of quantum magnetism, sometimes called the quantum compass model. So these are systems where the interaction that you get depends on the direction in space, and this dependence on space is kind of like a rotation in this internal space here. So 120 degrees quantum compass model, to be more precise. Yes, so that was the model, and now what we do is, let me just emphasize that in the Hamiltonian that I showed before, you notice there was an S.S coupling. So this model actually has an SU2 symmetry, which is not the original spin SU2 symmetry. It's a kind of hidden SU2 symmetry that appears in this kind of system when you have just coupling between, the dominant coupling is between two XY orbitals on the XY plane, and you project this to a low energy manifold of the J equals 3/2. This is not a very robust symmetry. If you add perturbations, other kinds of interactions like Hund's coupling to this model, this hidden SU2 symmetry will be broken. But it's there for the simplest Hamiltonian. And in addition, there's a crystal symmetry. There's a point group OH. And in particular, there's a Z3 symmetry that tells us that we rotate these tau alpha beta pseudo-orbital operators together with the planes. With the symmetries considerations, you can then actually write down a representation of the J equals 3/2 operators in terms of Majorana fermions. Now, to represent 4 states, you actually need 6 Majorana fermions, and they're represented like this. The pseudo-spin S is mapped to the product, some bilinear of Majorana fermions called eta. The pseudo-orbital operator is mapped to a bilinear of theta Majorana fermions. And again, we have a local constraint, it's like a Z2 constraint. And then what we do is that we plug this Majorana fermion representation into this model for double perovskites. In this case, the model is not exactly solvable by this representation, so I have to do some mean field theory. And this is a mean field theory for spin liquids. And the standard thing to do is to define these things as the order parameter. So these are the expectation value of the Majorana operators at different positions. So typically, when these things are different from 0, it tells you that the Majorana fermions are deconfined. There's some amplitude for them to hop around the lattice, and you should get a liquid of these things. Here we impose that these are going to be the order parameters, and we try to constrain them by symmetry, like translational symmetry. We want to preserve this hidden SU2 symmetry, the Z3 pseudo-orbital symmetry, and as many symmetries as possible. But it turns out that when we try to impose the ansatz, the pattern for these order parameters on the lattice, we have to break the FCC lattice into 4 sublattices, painted in different colors here. And you always break time reversal symmetry and a reflection symmetry. The way to see that it breaks time reversal symmetries is just like you can plug in that representation and show that this operator here, this is the scalar spin chirality, a triple product of 3 spins around any triangle here. This operator acquires a non-zero expectation value. And this is a well-known order parameter for a chiral spin liquid. Chiral here refers to the fact that it breaks a reflection symmetry and also a time reversal symmetry. And when you do this mean field theory, then we can calculate the spectrum. We get some mean field Hamiltonians for the Majorana fermions that look like this in momentum space. You can write this in terms of some matrix HK. And the interesting thing here is that you can write this HK in terms of 4x4 matrices that anti-commute. And these are functions of the momentum in the Bridwan zone. And the fact that these anti-commute tell you that this kind of looks like a Dirac Hamiltonian for a massless particle, except that the function of momentum here is not just k, but some function with the symmetry of the lattice. So there's a cosines of k's. And the spectrum that comes out of this is represented here in this picture. These are high symmetry lines in the Bridwan zone of the cubic lattice. And the important thing is that the spectrum you get is gapless, but because these are fermions in 3 dimensions, usually what you get in a gapless state is a Fermi surface in the 3-dimensional Bridwan zone. However, here in this case, what you get is that the zero energy states are along lines in the Bridwan zone rather than surfaces. These are called nodal lines, and in this case, they lie along the edges of the Bridwan zone. And if you take the dispersion relation perpendicular to any of these lines, like moving along this direction, the dispersion is linear. So it's like a Dirac Hamiltonian with linear dispersion, very much like a cut of this would be like graphene. And these lines cross at some point here, this vertex R of the Bridwan zone. And about that point where the lines cross, the dispersion is parabolic. And this is important for the low energy density of states of this system. So yes, let me just add the comment that these nodal lines, you can show that there's some kind of topological defect in momentum space. In this case, they have to be protected by symmetries of this chiral spin orbital liquid. But there's some analogy with line node semimetals and superconductors that people have discussed in the context of non-interacting systems. This would be like a Mott insulator or a strongly correlated version of these phases. Oh yes, like I said, so because you don't have a Fermi surface, you only have bend touching along lines, in particular this crossing at one point. That's what controls the low energy density of states, and the low energy density of states vanishes at zero energy. And this is something good from the point of view that if you want to take this model beyond the mean field level, you can argue that this chiral spin orbital liquid is going to be stable because with the vanishing low energy density of states, interactions between Majorana fermions are going to be irrelevant in the sense of the randomization group. These will be short-range interactions. They would be irrelevant. Just from the exponent here, the density of states for a single fermion goes like a square root of energy. You can predict that specific heat, how the specific heat should scale with temperature in the low temperature limit. You get something like T to the 3/2. So what we did after this was to try and calculate some properties that we can predict from this theory for the spin orbital liquid. So the first thing was to calculate the specific heat at finite temperatures. And basically what we do is that we solve self-consistent equations for the spin liquid order parameters at finite temperature. Once you impose symmetries, there are essentially 4 order parameters, and this is how they behave as a function of temperature. They all vanish here at some critical temperature, and in fact, for this system, we expect a finite temperature phase transition because although this is a spin liquid that doesn't break SU2 symmetry, it breaks time reversal symmetry. So there is symmetry break here, so we expect some kind of second order phase transition at some critical temperature that you can actually predict or approximately from the field theory. And if you use these order parameters to compute the specific heat at finite temperature, you get a curve like this. So the specific heat would drop here at this critical temperature. And on this side, I'm showing the experimental plot for barium, yttrium, molybdenum oxide that I had before. And if you believe in that, or if you agree that this kind of looks like the experimental result, we can actually use this sharp drop of the specific heat to fix the energy scale, the only energy scale of our Hamiltonian. That's the exchange interaction J, which here would be of order 72 milli-electron volts, and use this estimate to compare with the other experiments. And the next thing we do is to look at the spin-lattice relaxation rate that is measured in NMR. So here, the interesting thing is that 1/2(1), you can relate to some dynamical correlation function for the J plus or J minus angular momentum operator. This is the operator that represents the magnetic moment that it's going to flip. And you can write this in terms of Majorana fermions in this spin orbital liquid phase. And essentially, this is a correlation function of free fermions. So you can get the result as a function of temperature again. And what we find is that the spin-lattice relaxation rate actually drops very rapidly here at the energy scale, which was the same as the drop in the specific heat. And this is a very fast drop, and this could be misinterpreted as a signature of a spin gap. Usually you try to fit an exponential to this thing, but remember that this is actually a gapless spin liquid phase with nodal lines, but it has a vanishing density of states. So one thing we're trying to say is that maybe you can still have a gapless phase to describe the system. It's just that the low energy density of states goes to 0, and then that would be consistent with what people see in the experiment in NMR. And the curve to see here, the red points that they see, is the singlet-like peak observed in NMR. Another property that we looked at was neutron scattering. The thing to compute here are dynamical structure factors for the total angular momentum operator. So here I'm showing the SZZ, which is the dynamical correlation function for JZ. This is the Fourier transform of JZ. And again, this is a correlation function that you can express in terms of fermionic operators. And the elementary excitation that we create here at 0 temperature are pairs of these Majorana fermions, like particle pairs. And this is showing the intensity of the dynamical structure factor as a function of momentum along high symmetry lines in the Bridwan zone of the FCC lattice, and as a function of frequency. And you note that the highest intensity here is along the is at this L point. That's the 1-on-1 direction, and some energy scale that matches the bandwidths of the Majorana fermions in our system. Yes, but to compare with available experimental data, there have been only neutron, powder samples used in neutron scattering. That means we have to average. We don't have information about the direction for the scattering. We have to average over angles. And in this case, that's what we do here. Integrate over a sphere for some Q in some range. And in this case, you get a single broad peak in the cross section. However, what they see in experiments is actually something that looks like this. There are 3 magnetic peaks. The one, if you use the value for J, the one that we would predict is only around here, this middle one. So this is a failure of our theory. We cannot explain 3 peaks in the neutron scattering experiments. I should say that our theory actually has multiple energy scales because there are different flavors of Majorana fermions and so different bandwidths. But all of them, they are very close to each other. So when you average things over angles, you only get a single peak here. So this does not work very well. So there's a question of what this higher energy peak here could be, and so that's an open question. And also because this other energy scale is not seen in the NMR or specific heat. So we started wondering if it would be possible to actually probe different energy scales that we have by considering other dynamical structure factors. So the results I've shown you so far are all expressed in terms of properties of the total angular momentum J. But remember, these are spin 3/2 operators, and for spin 3/2, it can have higher multiples, things like J squared or J cube operators, is with quadrupole and octupole moments of the spin. And in fact, you can express organize these higher multiples in terms of irreducible representations of the octahedral group, and here write them in terms of pseudo-spin and pseudo-orbital operators in our language. And if you like, add another column here where they're written in terms of Majorana fermions. And in fact, there is a way to probe different excitations, and that's resonant inelastic X-ray scattering, kind of experiment that is becoming very popular for strongly correlated materials. And this is essentially some experiment where you do scattering. There's a photon in, photon out response, and you treat the coupling to the electromagnetic field. The resonant here in the name refers to the fact that you tune the energy of the incoming photon to coincide with the energy of a core hole that you create. And in that case, the second order process is more important when this difference is very small, more important than the first order process. And within a lot of our approximations, you can really express this in terms of some dynamical correlation function, some structure factor with some operator here that depends on your choice of the polarization of the incoming and outgoing photons. So this here is something you can in principle choose by selecting polarization. So let me just give you a couple of examples. So one thing you can probe now from combinations of polarizations is the dynamical structure factor for the pseudo-spin S, which was different from the total angular momentum J. And remember that in this case, the pseudo-spin operator has a hidden SU2 symmetry, and this would show up in the dynamics because when you have an SU2 symmetry, something you can predict is that for Q equals 0 scattering, that is the gamma point in the Bridwan zone, the scattering cross-section vanishes. And that is really true here in the calculation that we can do within this mean field theory. And here's another example for something that only involves the pseudo-orbital operator tau x. And you see that the energy scales are really different. This guy would excite different flavors of Majorana fermions. and the distribution of a spectral rate is really different. So in principle, you take combinations of these things, you could probe different excitations. And with that, I will conclude. So the main message is that, again, you can find some new spin models with bond-dependent exchange interactions by considering Mott insulators with strong spin-orbit coupling. And we have talked about this case of a possible gapless chirospin orbital liquid and barium yttrium molybdenum oxide. And the more recent results are about these dynamics, and where we learned that actually RIXS can probe different pseudo-orbital and pseudo-spin excitations, and in our case, these are different flavors of Majorana fermions. So thank you for your attention.